Hello, everybody. Thank you for funding this room that I almost did. Very happy to have a lot of people here. Even if this session is just after lunch, so I suppose everybody's a bit sleepy. So I try to keep you awake. So this talk is about functional programming. There will be some example of code in Kotlin. How many of you use Kotlin? I mean, more fish. But I mean, I hope the code should be quite easy to understand from Java point of view. How many of you knows Java? Okay, yeah, that's better. Just Kotlin, it fits better in the slide because it's more compact. But there is nothing that you cannot do in Java itself. But Kotlin is really nice. You should try that. So let's talk about this talk. And funnily enough, I was here at the DevOps last year, and I was talking about similar things, category theory and functional programming. And, that's me. And then at the end, someone asked me, you said that you are a passionate programmer, because I really am. I'm very passionate about quality. And you're talking about code quality, you are talking about category theory. What are the relations between the two? And I thought, this is a really, really good question, actually. So the quick answer is that when we studied object orientation, we studied, I hope you studied the design pattern. At least for me, it was a very, very important book to study. When we do functional programming, we should study category theory for the same reason. I mean, you can do without studying, but if you study, you can do better. It's a bit like... Okay, that was my talk today. I told you. Thank you for coming. Okay, let me expand a bit on this. So basically, the idea is that the categories. How many of you know about the word category theory? Okay, so, and how many of you know about do functional programming a bit? It's good. You're in a good place. Perfect. And you may have heard about the category more in this talk. And the thing is, if you are struggling with your functional programming design, you want to do functional programming, but you, for example, with the design that is not really what you see in the books of functional programming, say this is very different. Then it's studying category theory can help you, but you don't have to go all the way through. It's still left other two questions. I mean, why functional programming at all, and how categories can help. On the why functional programming, I think the only answer is that it's not that functional programming is going to replace object orientation, or object orientation is bad and functional programming is good, or the opposite. Is that there are very different paradigms, and each one has some fields where they shine. There are some things that in object orientation is definitely much faster and easier to do, more natural. Some things that in functional programming more faster, more easier to do. For example, I forgot the name of the gentleman before me was talking about Kafka, and if you have some Kafka reactive stream, stuff like that, functional programming is very, very effective. But for other things, if you do, I don't know, UI, for example, complicated UI, object orientation is definitely the best. So it's not that I want to say everybody should do functional programming. But if you do functional programming, why studying category theory? And then we go to what is a code quality, because the alternative of good design is spaghetti. I'm from Italy, so I know about spaghetti. And you may have heard of the 4 rules of simple design, which this Kent Beck wrote many, many years ago. I don't remember. And they will say that to have a good design, there are basically 4 simple rules. The code should pass the test, because if it doesn't work, it's not only if it doesn't work. If you are not proving that your code is working, you have a bigger problem. You shouldn't worry about quality. First make it work, and be able to prove that it works. The second point is reveal intention, because we want that our code, when you read our code, you can understand who wrote that code, what it was thinking about, what it was trying to do. That is important. Just slightly less important is no duplication. We don't want duplication is not only copy-paste of code, but is expressing the same things multiple times. If we have a place where we decide if something is A or B, I don't know, if there's a customer or an internal admin, there should be another place in the code where we are doing the same reasoning. We don't want to repeat ourselves. And all these things being equal, the less code you have, the much better. These are quite simple. And the funny thing is, they work perfectly well also with functional programming. So you don't have to change the rules to make work on functional programming. They work exactly the same. They are completely independent from the paradigm. But the other thing that I want to say is that functional programming is a paradigm of programming. It's not a library. It's not a language. It's not something that I'm doing Lambda, so I'm functional programmer. No, it's a paradigm. It's something that you have to think in a different way. And you may know about these 2 guys. How many of you know? Oh, well, yeah, you should study functional programming history. History is important. Basically, the guy on the left, Alan Key, is the guy who basically invented object orientation programming. And the guy on the right is the guy who invented functional programming. And the funny thing is that functional programming is actually older than object orientation programming. But then things change, and then that was in the 60s, so of course now it's much more complex. But for me, in my personal story, after the university, these 2 books are the 2 books that forced me to think again about functional programming, coming from an object orientation programming background. The book on the left, how many of you knows about? How many of you knows about the book on the right? Yeah, no, there are very 2 books. The book on the left is how to use object orientation programming with a bit of functional programming, combining the 2 things. The book on the right is functional programming on Scala. Very, very hard. But after reading this book, I started to see categories everywhere. So I went to discuss these things with some example today. But at the end of the day, let's remember that the proof of the pattern is in the eating, how they say, and the functional program is in the coding. You are not a functional programmer because you write Haskell. It's perfectly fine. It's perfectly possible to write a terrible imperative code in Haskell. I know because I did. So, I mean, it's not a language. It's not a library. It's the code that you write and the way that you think. And this is our tool of the trade. To do functional programming, we need higher order function, that let's discuss later, immutable data, and laziness. But at the end, it's all about morphism. And if you know this guy, this is another book, the last book of the talk. If you are really want to learn category theory, this is the best book ever. It's also free on internet. It's quite complicated, but it's definitely worth. And at the end, it's all morphism. All the concept of functional programming is around morphism. If you grasp this concept, you should be able to write functional programming, whatever the language, whatever the library. And let's see some example in morphism. Morphism is something that take a type and transform in another type. So far, so good. I mean, data string, user date, user is whatever you want it to be. But it can also be a function to another function. So we can have a function that take a user transform in data, and now we transform in a function that take a user transform in a string. So this is the idea of morphism. And you can see any normal function that we use in Java is perfectly can be a morphism. The important part is that must be pure. So if we call a string and then length, we are sure that if the string is hello, the length will always be, 5. Always be 5. There is no way that, I don't know, there is a configuration, so hello will be 7. No, this is a pure function. So in fact, instead, if you go to the DB and you say, what is the value of user 123, depends on the DB that you have behind. So it's not a pure function because the output of the function is not only depending on the input, but also from external things. Instead, to talk about morphism, we will only talk about the pure function. And since we are talking about category theory, let's see what is a category. Basically, to make a category, you need 5 things, which are quite reasonable. You need some object, some arrows, and make sure that each arrow just connect one object to another object. Object here is not object in object-oriented. It's object like mathematical something, stuff. And arrows is just one-to-one, so it's not strange arrows. And then all the arrows must be composable. So if you have an arrow that from A go to B, another from B to C, you must be able to combine them. And the result of combination must be exactly the same as it was a single function. You cannot really. These are kind of rules. So you cannot have something like get user from DB because that will be different every time you call. But if you have something string length, that will be okay because string length and then you have another function that plus 2, it will be always the same. And then you need a kind of identity function, which is not. So just this is the basic recipe, very simple things. And you can really, this is a mathematical concept. It's completely abstract from any content. We are finding useful in functional programming, but it can be, it's used in, I don't know, high-level physics, stuff with the quarks, stuff like that. I have no clue what they are using for, but it's useful. So it's very concept, a general concept. But just to make an example, we can make an example with the London Tube. We can see the tube as a category, because we can go from a station to another station. The station are the object, and the routes are the arrows that connect the object, and we can connect the arrows, and the result will be absolutely identical. And if we stay in the same station, it's kind of being an identity. So category is something very, very generic concept. And if you know about event sourcing, you can also have a category with your events that transform the state of the object. That's also be a category. So a category is not only something that in the Haskell language you have this called category or whatever. It's a mathematical general concept. And a friend of mine, you know what is called kata? The code kata are a kind of exercise to learn how to code. So the idea is that like in the martial arts, you have the kata. You have the same things in code where you do some kind of simple exercise over and over again so you can improve. And he wrote this exercise for object orientation. And the idea is that you have a file with some dates, some data from a user, and we want to send an email to the user where today is their birthday, basically. And I mean, if the slide, if you read his blog, it explains how to do in object orientation design with hexagonal architecture. You know, a kind of common technique for object orientation design is take the specification, identify the names. The names could be potential candidates for objects, and then the verbs are potential candidates for methods in those objects, and then try to figure out how to make the domain work. But we are not doing that, because we are not doing object orientation. We are doing functional design. And we have a three-way process. Functional type, pure function, immutable type, I think it's quite easy. Sometimes we don't want stuff to change, because if you say that something is something, we don't want it to be able to change. If we say that 5 plus 2 is 7, you cannot change 5 and then make now 5 is 4 and make no sense. So every object must be immutable. We have functional. We have a laziness that helps us to simplify things when we only evaluate things when we need them. Well, actually, there are 4 weapons. And we have no exception. Because also the exception are kind of breaking the flow. Instead, we wanted to keep the flow. The only kind of exception is something like you want to divide by 0. Those are kind of errors, and of course you want to stop the program. But we don't use exception to model the flow of information. For example, just to make a specific example, if you use a Spring Boot and you want to say that something is not authorized, you need to throw an exception. Last time that I check. This is not how we do stuff in functional programming. And how we model stuff. So basically, at the end of the day, we needed to deliver value to the customer, because that is the point of writing code. It's not that an academical exercise. So we have this kata that we want to do. So we have a file name somewhere where we can get the email, and at the end we have the email sent. And this is, I think, more or less, we agree on this. And then how we can, this is how I try to say, okay, but we can be a bit more precise. I mean, for a file name, we can actually take an actual text. We can get the email data, and then we have the email sent. But if we dig even, we can see that the text is making by some row with a comma separate value. From a row, you can get an employee. From the employee, you can get the email data. And so you can describe more exactly what you want to do. And the point is that as smaller you can do this smaller morphism, transform one thing to another, the smaller will be your function, the easier will be to combine them. Because the great advantage of functional programming is combining this morphism one on the other, rather than just to have 300 lines of code of a function that do something. Because it's really important to have this idea of combining stuff, moving stuff around, see the result, how it comes from some input to some output. So at the end is kind of a tree. And now, hoping that nobody's sleeping yet. So this is more or less a kind of a cascade. But what is missing to do this? We need some more. We have the input file name. The output is the email sent, but we actually need something else. There is another input for this stuff to work. Yeah, exactly. So we need to specify what is today. Because also the time is an external thing. It's not, must be explicit in the input. I'm doing this stuff every day. It's not completely academic stuff for me. And what I think that when I go in this kind of reasoning, I discover much better what are the requirements of my code. So I avoid a lot of bugs just because I have to think more about the code when I write the code. Otherwise, it doesn't compile. And another thing that you can see is that we try to avoid general stuff like a string or integer or general type that doesn't have a specific domain value. So even if our file name is just a string, we want to have a type called file name. Because if we have a function that takes a file name and return a text, it's clear that the file name is a string, but it's clear that it's a file name. If we have a function that takes a string and return a text, we have no idea what that function is doing. So having a special type for each step of our transformation is very important. It really helps us. And this is how the code looks like in Kotlin. Well, basically, this data class is probably will come in Java soon as Project Valhalla with the inline classes. But the idea is that it's just a class with like a POJO, immutable POJO. It's just more compact. And you see that the morphisms are just a function, basically where you can, for example, take an email template and return an employee to email. So you create a function with the function, with the class. If you want, all the code is on GitHub, so if you wanted to look at later. I know that you cannot really understand the code when you see the slide, but if you to have just a look at how it looks like. Okay, but so far so good, let's assume. What about all the other stuff? Because it's easy to say, okay, I don't want to use a database, but at the end of the day, we're using database. We're using collection. We use I/O, errors, time. And the idea is that basically some transformations are kind of transformation in the same category. And that's kind of easy because you have a type and you return another type. But some transformations are transformation from one category to another. For example, if you have a list of rows and then you have a function that works on a single row, you need some kind of mapping between the two. They are not in the same set of rows with a single row. It's a different category. If you go on the I/O, it's kind of a different category. So we need something to switch from a category to another. Is it possible? And yes, this is the mathematical answer. It's called functors, which is just a funny name. I mean, it's kind of cool having these mathematical names. But at the end, it's just something that takes a function and return another function. So to have a small example, I used to work in Milano. Now I work in London. And there are some similitude between these two cities. They have both kind of a main church, which in Milan is Duomo, in London is St. Paul. They have a castle. They have the Royal Palace. And we can imagine that Milano has its own category, and London is another category, similar. And the functor is something that takes one object from one category and map to another object to another category. But it maps in a way that preserves the category structure. And not only functor maps objects, they also map arrows, which, to be honest, is more interesting for us. So if we can say that the arrow is the work that I do from Duomo to Castello, a functor can transform in a work that I do from St. Paul to Tower London. And also, you think that it's not that the category is something that is ontological true or something like that. No, it's something that it's only convenient for us. We can say, no, we wanted to map Duomo to Westminster Cathedral. That's perfectly fine. It's only something that makes sense for us to solve our problem. It's not something that we wanted to discover any hidden mystery or whatever. So we just wanted to have this kind of reasoning, which is actually very useful. And the simplest possible functor in our code is just when we do a length of a string. Because when we do a length of a string, we map from the category of the characters to the category of integers. So each character we can combine together, the integer we can combine together, and so we can see the string length as a functor between this kind of a category. But this is just an example, just to show that functors are not something that you need to use the functor library. Anything is a functor. But, okay, string length is not really reusable. It doesn't combine very easily with other stuff. What instead is quite useful is the thing that we call generics. Now we are at least I was used when I started generics in Java 5. To see generics as something very complicated. But the functional way to see generics is very easy. Generics are just a type constructor. So if you have a list of T, you don't have to think about the list of T as a type, but just a type constructor. The actual type will be list of string, double, employee, whatever. So list of T is just your constructor, basically. And then from template, in C++ they are called template for a good reason. And from that list of T, you can generate all the type the real type that you need. But you can already probably see that there is some relation between a string and a list of string. They are not the same things, but they have many things in common that a list with a string with a list of integer doesn't have, for example. So there is a kind of a relation. And this is the kind of relation that we are trying to explore and bringing out with the category or with the functor. So if we have something that take an employee and return a list of employee, which in this case probably we have just one employee, but is the type that we really care. This is actually a functor. And the list, there are many functors, many common functors. If you take one of those books, they have a list of common functors, plus all the functors that you may need in your specific code. But the list is probably the simplest non-trivial functor. The other, can you imagine another functor in Java that quite recently? Yes, optional. Optional is another kind of functor. And there are also other we see, but this idea that you take a type and return another type, but it still have some kind of relation with the original type. And this is how, basically, once we have the functor, I have the functor. Or mathematically speaking, we say we have a functor instance. We can say, okay, how we use the functor. And we use the functor with the map. That is, in Kotlin is nicer, but there is also in Java. So you can say, I have a string called list of string. I have a function that takes a string and return an integer. I want a list of integer. And we have our functor that can do that. Because it just in this specific case, it will just apply to all the list and the int. Is clear? Any question? I see some people. I know that it's heavy. We just eat. It's food for brain. You need to think in it about. But this is really important because all this stuff, monads, fancy, complicated, reactive. At the end, it's just this one. This idea that you take a type and you transform another type, but you preserve some property. And the other similitude is that functor is a bit like a forklift, because you have a function from an employee to a string, and you transform in something that from employee, list of employee to a list of strings. And it can be an optional employee to an optional string. It can be a reader of employee to a reader of string. It doesn't matter what is the functor, but we transform our object. We lift the function, basically. And any functor can lift the function and transform in the other category. One possible problem. Okay, but what do we finish to do? I mean, we have a string of list, a reader, a list, a result. Very, very complicated. There is also a way to simplify things. We are not only overcomplicating them. Well, sometimes we complicate, but sometimes we also. And you know, if you have a category that has only one object, so all the arrows go to the same object. And also, since the object is a type, it's not that the arrows are all identical, because you can have an integer, and it can be an integer to an integer, but the actual, the type is the integer, but the actual value can change. I mean, arrows work on types, not on specific. So you can have 1 arrow that do, I don't know, +1, +2, +3, whatever. You know what is called? Monoid? Yes, perfect. So the monoid is a category where basically you have only one object. So monoid. It's quite easy. And the idea of a monoid is that since you have only one object, so you have something that goes from integer to integer, you can kind of reduce. If you know map reduce, the reduce part is related to monoid, because we can reduce. So if we have a 50 integer and we have a monoid with the plus operation, we can just apply plus, 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 plus. At the end, we just have one number, which is the sum of all our integer. So the monoid is, because it's these things that goes again, and you can keep applying, you're reducing your actual set of starting point. Yeah, for example, you can have with integer, you can do a sum, with a string, you can concatenate them. So we talk about functor, but if a functor have the same input as output, it's called EndoFunctor in a mathematical point. So if we do the same things and say, instead of talking a category with only one arrow, we talk in a category with all our functors, but only one object. And of course, that is called monad, yes. This is called the famous monad, if you know. So basically, when we wanted to reduce some number, we can use a monoid. When we wanted to reduce some functor, we use the monad. And the monad is something that, for example, you take a string and you return a list of string, just to make it simple. And then you have another function that takes a string and return a list of string. But when you put it together, you don't want a list of string. You just want a list of string. And this is what the monad does. You just combine the two functors in a way that you have a single result. So one also very common way is that you have some result that can be positive or negative with a different type. So if you keep applying function on function, you will have a result of result of result of result. But of course, at the end, you just want a result, either the final result or some failure. Let's see some example. Don't know if you can read. Yeah. But for example, this is how you use a functor to have a filter. So you have a list, you return another list, but only with the element with the same born in the day of today. So you keep using this transformation. This is from a list to a list. But this is what I was talking about, errors. Okay, sorry, I didn't put here the code for the monad, but there is, if you look at GitHub, there is. So basically, you have an error that is called an outcome. No, not an error. You have an outcome that can be either an error or a value. And you can transform the error or you can transform the value, combining them together. For example, just to give an example, you have something that goes in a website, return some text. But it can either return the text or return an error that the website is not up or whatever. Then you combine, you take the text and you do another transformation, and you still have another result. Essentially, this second transformation went well, this is the result, or this is an error. And then you can combine them together. But yeah, you can do. Or also, for the same things, you can do also with exception. Try to do this operation. If it goes well, return the result. If there is an exception, return the exception as an error. This is different from letting the exception go up. Basically, you wrap your exception in a result, which is useful if you, for example, if you use other Java library that use exception. Any question? I think everybody's sleeping now, but. And you can also use functors or monads to read from I/O, because of course at the end of the day we need to read from I/O. I mean, if you do a perfectly pure program, it cannot read any input, it cannot produce any output, so it will be completely useless. At some point we needed to go dirty and touch the I/O, but we use a functor. So in this way we keep the I/O dirty code completely separated, but our logic, which is completely pure mathematical way. And you can see this as I put the bad part under the carpet, but it's really more like let's keep completely separated. Let's keep a wall between what is implementation detail, what is domain logic. And the domain logic can be used by much better, because you have the transformation, you can read from a file, you can read from a web server, you just need to change, for example, in this case, the reader, functor. And you can keep, if your logic will be identical, you just change the reader that you use. And you can reuse the same reader for any kind of reading from a file, for any kind of reading from web. The other one. So you can be more finer to reuse your code in your code base. Also, by the way, not having exception, it really helps in this case, because if something fails, you just return something that can be still transformed and reused. Instead, if you have a function that can return an exception, you are never sure where I can use this function, where I cannot use, because will return an exception, will break everything, or maybe in this case it's okay an exception, because it really depends. For example, you have a website where it loads for each line some other info, but if the other call fails, you don't want the website, the page stopping displaying. You just want a small error. Much easier to do. And this is, for example, the result, how we use how all this stuff came together. So the final code for the kata is just this. you can just read basically, you get all the input, and then you have a map, a filter, map, filter to list, and that's it. And can be kind of scary at the beginning. I don't know, how many of you think this is a good thing or a bad thing? How many of you think it's a good thing? Yeah, but it takes time to be used to. But I really like, and it's really easy to compose. But yeah, okay, so let's make some clear. So this will be the main function from the main, and these are all our functors that we use to solve. And this is how we go back to the 4 rules of simple design. And you can see that passes the test. Actually, doing unit testing in functional programming is very easy, because each function is very easy to test. There is no dependency, hidden dependency. There is no hidden state. Everything is much, much easier to test. That's definitely an advantage, but it's really important to write the test anyway. Reveal intention. Sometimes, it's important that your functional code still reveal the intention. It's important that you write a unit test, and it's still important that you try to make your code. It can be unfamiliar, but if someone is familiar with this kind of thinking, this code is quite clear what it's trying to do, because it's mapping is the reader from the file, is mapping to employee, is filtering, then is transforming to template, and then to email. It's not trying to make something very complicated. I mean, it's still kind of reveal what we want to do, even if the syntax can be unfamiliar. But it's very important to try to do this, which is probably not as easy as in object orientation. But not duplication, that's also very important. The whole point of doing functional programming is to reuse the same function over and over again. When the red book that I showed at the beginning on Scala has some exercise how to transform a list in a map or whatever. And my first solution exercise was like 30 lines of code. Then I went to see the solution. The book is like 2 lines of code. And yes, this is functional programming, because 2 lines of code are using all the other function that was already created. Instead, in my 30 lines of code, I was rewriting them, basically. So the idea of functional programming is force you to reuse as much as possible and to compose the existing function. And then a few elements. Yeah, we also want, reasonably speaking, everything being equal. We wanted to have less code, less bug, less easier to maintain. And so, let's wrap up for today. I hope someone is still awake. And the functional programming goals are exactly the same as object orientation. You don't need a special language or library to do functional programming. You can perfectly do in Java. No need to have. I mean, can help. I mean, in Kotlin, some things are easier than in Java. In Haskell, are still easier, but other things are more difficult. But you can absolutely do everything in Java. But you need to study and to learn a new paradigm. It's not just, I just use Lambda everywhere, so I'm a functional programmer. And this is the GitHub with the code of the exercise. So if you have any question, I also have a kind of experiment. I will do some online course on basically the content of this talk, but practical. But please also follow me on my blog. I blog on this kind of stuff and on Twitter. And any question that you have, well, first today, but if you have some question later, please ask me on Twitter. Questions? everybody still, I know. Thank you very much for today.